So today we are going to discuss about Carnot engine. Okay. So Carnot engine is a ideal reversible engine. Okay. And before studying Carnot engine, in previous days we have discussed about first law of thermodynamics, second law of thermodynamics, and we were just yesterday we were discussing about reversible and irreversible processes. So it was quite essential to tell you what is reversible and what is irreversible because Carnot engine is an ideal engine where the processes, all the processes are reversible. Okay? So reversible processes are the processes where there is no dissipative effect and where each processes are quasi-static in nature. So always there is equilibrium between the system and the surrounding. So that is the reason why we had introduced reversible and irreversible process and isothermal and adiabatic process and the work done in isothermal and adiabatic process. Because to derive the efficiency of Carnot engine, we need to know what is the work done. Because without knowing the work done, we cannot derive the efficiency of Carnot engine. Okay. So, Carnot engine is an ideal engine operating between two temperatures and it's a reversible engine. That's the definition of a Carnot engine. First, it's the ideal engine, number one. Number two, it operates between two temperatures. Two temperatures, source temperature T1, sink temperature T2. Number three, it is a reversible engine. That means you are taking heat, getting work, giving heat. You can reverse the process also. Okay, you can reverse everything. Okay, so that's why these three things are important. It's an ideal engine. It's operate between two temperature. One is T1 and another is T2. Source temperature T1, sink temperature T2, and it's a reversible engine. So we have discussed what is irreversibility. So irreversibility is where you have dissipative effect, like frictional loss or any other loss. I was telling like if a body is moving at certain velocity, let us say a square body is moving at certain velocity, then after some distance it will stop. Why? Because there is friction between that body and the surface. So that friction, because of friction, the it, kinetic energy has become zero after certain distance. So that friction effect, because of that friction effect, there is a dissipative effect, and it has got converted to the heat, and then the body has come to standstill. Okay. So reversible process is quasi-static and non-dissipative. Means there is no loss, no frictional loss or any other loss in case of reversible process. And it is quasi-static, very slow, very slow. It is quasi-static. Static, quasi means almost static. Okay. So if there is a finite temperature, so when we how will Carnot, the French scientist, before arriving at the cycle, he told like the concept was which process can be reversible, which process can be reversible. So that when a reversible process happens or a quasi-static process happens, there is hardly any temperature difference between the source and the system. So he told the first process has to be isothermal. So this first process has to be isothermal. Okay, so here he is taking heat. Here he is taking heat E1. So this is your working substance. It is it, the source is at T1 and the working substance is also at T1. Okay. So they are almost at equal temperature. Heat transfer is happening, but it is almost at equal temperature. That means it is absorbing heat, but there is no finite temperature difference between the source and the working substance. It is observing it, but it is happening so slowly that the temperature of the working substance from 1 to 2, this is 1, this is 2, this is 3, this is 4. So in a isothermal process, there is a heat transfer happening between this source and this ideal gas. The working substance here is ideal gas. So there is some heat transfer happening between the ideal gas and the source, but that is happening isothermally. It means there cannot be any heat transfer if there is no temperature difference, right? Any heat transfer needs a temperature difference, but if you make it very very slow, if the if you make it very very slow, so that there will be some heat transfer happening, there will be some heat transfer happening, but the temperature of this source and this working substance will remain same. If you make it very slow, right? Quasi-static. So, Carnot said that this absorption, there are two isothermal expansion and this is isothermal compression. Why it is expansion? Because V2 is greater than V1. Why it is compression? Because V4 is greater than less than V3. Okay, so this is this, like this it will go, like it is a cyclic process. So this is isothermal expansion and this is isothermal compression. It and here in this process, heat is coming from the source at T1. Okay. And in this process, heat is going to the sink at T2. Okay. So the heat transfer is happening quasi-statically, so that there is no finite temperature difference between the source and the working substance, that is the ideal gas. So only isothermal process, in isothermal process that can happen. So Carnot said, okay, there has to be two isothermal process. One is isothermal expansion, isothermal compression, where he can make the process quasi-static so that it can become a reversible process. Okay, so reversible means what? Suppose it has gone to this, it can also come back from 2 to 1. Okay, it can come back from 2 to 1 without any dissipative effect. So whatever heat you have observed, you can get that heat back also. That is, if you do it quasi-statically. Okay. So reversible process is a quasi-static process and non-dissipative process. If you have dissipated something, how will you bring it back? Yes. Not possible. So it has to be slow and it has to be non-dissipative. Okay, so he told, okay, isothermal process can be something like that. Okay, when there is no finite temperature difference between the source and the ideal gas, which is the working substance. Okay, so here system at T1 absorbs heat from reservoir at T1. So ideal gas system is nothing but an ideal gas. Ideal gas at temperature capital T1 absorbs heat from reservoir at temperature T1. Similarly, system is nothing but ideal gas at T2 rejects heat Q2, Q2 to reservoir at T2. So it takes heat Q1, it gives away heat T2, it gives away heat Q2. So it takes Q1, it gives Q2. So these two, what is happening is isothermal absorption or rejection of heat. Okay. So with that, so let us draw the PV diagram of the Carnot cycle. Okay. So we know it contains four processes. Okay. It contains four processes. So from 1 to 2, it is isothermal expansion. From 2 to 3, it is adiabatic expansion. From 3 to 4, it is isothermal compression. For 4 to 1, it is again adiabatic compression. Okay. So now our aim is to derive the efficiency of a Carnot engine. You should be able to derive it. So for that, we need to know, we have already derived what is the work done in isothermal process and what is the work done in adiabatic process, right? So we have already told that efficiency is nothing but work done by Q1, right? So it is, otherwise it is We know we know that efficiency is equal to work done by Q1. Q1 means what? What? How much heat you have taken? W is what? How much of that heat you have converted to energy? So efficiency is nothing but work done divided by Q1. And again, you know work done is equal to nothing but Q1 minus Q2. Right? You know from first law of thermodynamics, like uh, Q is equal to U plus W. Right? So in this case, because it is a reversible process, Q is equal to 0. Right? So Q is equal to W. So work done is equal to your actually it is del Q. Okay, del Q is equal to work done. Okay, del Q is equal to work done. So how much is del Q? It is nothing but Q1 minus Q2. Okay. So always remember work done is equal to Q1 minus Q2. So that is from first law of thermodynamics. So for Carnot engine, first law of thermodynamics is the driving factor for any heat engine or refrigerator or whatever. So you know work done is equal to Q1 minus Q2. So you have told, okay, my efficiency is equal to Q1 minus Q2 by Q1. Okay. So your efficiency, if you simplify it, it becomes 1 minus Q2 by Q1. Okay. Then uh, yeah. So you know, um, for the first process, say process 1, 2, that isothermal expansion. So whatever work we are doing, that is same as heat received. Because first process, you are receiving some heat and some work is being done. So work done is equal to heat received. Okay. So and you know that I have already derived that work done for a isothermal process. Okay, that is like mu r T1 ln V2 by V1. Why is it so? Because we have derived like PdV V1 to V2 in isothermal process. Okay, P is nothing but a constant divided by V into dV from V2, V1 to V2. So it becomes dV by V, K go outside. So this Q, K is nothing but a nu RT. So, so from that, you know, work done in isothermal process is nu RT1 ln log dV by V integration is ln. Okay. So nu RT1 ln V2 by V1. That is the work done in the isothermal process. Similarly, for the other isothermal process, that is 3 to 4. That is the other isothermal process. There are 4 processes happening. The other isothermal process, the work done is nu RT2 ln V4 by V3. Okay. So that is the other work done. And in the adiabatic process, 2, 3, and 3, 4, the work done we have already derived something similar to this nu r T1 minus T2 by gamma minus 1. That you should remember, you should know how to derive. You should be able to derive that. Okay. Similarly, W4 to 1, nu r T3 minus T4, a similar expression, nu r. So because T3 is equal to T1. What is happening? You can see here like 1, 2. So T1, T2. Okay. Uh, say, so actually T3, you know, like, yeah, or T1 is equal to T3. So you know T1 is equal to T2, right? T1 is equal to T2, you know. Then T3 is equal to T4, that you also know, right? Yes. So if T1 is equal to T2 and T3 is equal to T4, then T1 minus T3 is equal to T4 minus T2. Right now, if this is equation 1 and this is equation 2, if T1 is equal to T2, T3 is equal to T4, then T1 minus T3 is equal to T2 minus T4. Yes. Right now? So that okay. So we'll say T1 is equal to T2, T3 is equal to T4, then T1 minus T3 is equal to T2 minus T4. That implies T3 minus T4. Again, if you take it on that side, T3 minus T4 is equal to T2 minus T1. That is simplified. So T3 minus T4 becomes T2 minus T1. So this is the this is simplified. T3 T4 is simplified to equation like this. So you know now this term and this term are almost becoming same. So the because these two work dones are almost same, so you can the total work done is equal to this work done, this work done, this work done, this work done. Okay. So because this work done is expansion and this work done is compression, they will nullify each other. Because these two terms are same. One is expansion, one is compression. So they will nullify each other. So if they nullify each other, then your Q1 minus Q2. So you forget about this adiabatic one. You just think about these two isothermal one. So Q1 minus Q2 is nothing but 1 minus Q2 by Q1. So Q1 you know this term, Q2 you know this term. When you replace it here, so you will get 1 minus T2 by T1 into ln B4 by B3 divided by ln B2 by B1. So, uh, from this equation, like you know, in a isothermal process, not only PV to the power gamma is equal to constant, but also TV to the power gamma minus 1 is equal to constant. Okay. If you, that is PV to the power gamma can again be written in terms of TV, temperature and volume. So if you write it in terms of temperature and volume, then I'll explain you how it is. You can derive it actually. See, PV to the power gamma is equal to constant. So you want it to write in terms of temperature. So PV to the power gamma is equal to constant. So P is equal to K V to the power minus gamma, right? So in terms of P, you can write right? K, K, uh, K V to the power gamma. Okay. So this K, you know K you can write as nu RT, nu RT, right? So this nu R is constant. So uh, so actually, okay, let us write it like this. So PV to the power gamma is equal to constant. So P want to replace by nu RT, nu R by T into uh, P PV is equal to nu RT. Okay. So P nu RT by V. Okay. Right. Then P to the power gamma. Right. So your nu R anyway, this is constant. So this term is constant. This term is constant. So T B to the power gamma minus 1. Right. So if you want to write the equation PB to the power gamma in terms of TB to the power gamma T in terms of TB, it becomes TB to the power gamma minus 1 is equal to constant. Clear? No? How I have derived it. So nu R P is nothing but nu R divided by V. Okay. So nu R T divided by V. So nu R is constant. So V gamma divided by V. So V to the power gamma minus 1. So TB to the power gamma minus 1 is equal constant. So TB to T1 V2 to the power gamma minus 1 is equal to T2 V3 to the power gamma minus 1. So when it goes from V2 to V3, because at V2 temperature, when it goes from at V2 temperature is T1 only, because from 1 to 2 temperature remains constant, right? From 1 to 2 temperature remains constant because it is isothermal. Similarly, T2 V3 to the power gamma minus 1 is equal to constant. Similarly, this is for process 2-3. Okay. Similarly, from process 4-1, and this is 2-3 process. Okay. This is 4-1 process. For 4-1, you can write T2 B to the power V to the 4 to the gamma minus is constant. T1 B to the power gamma minus is constant. So when you simplify all this, you when you simplify all this, you will arrive at a equation V3 by V4 is equal to V2 by V1. So you know V4, V4, V2 by V1 and V4 by V3, these are constant. Like you can simplify it and you can find it out. So V4 by V3 is equal to V2 by V1. That means it is expansion. Okay. So actually uh, it is because V4 is higher than V3, right? So V4 by V3 it is common sense. V1 by V2. Okay, because V1 is less than V2, right? So V1 by V2 is nothing but V4 by V3. V1 by V2 is V4 by V3. So if that is the case, V4 by V3, V4 by V3 and V4 is less. So probably it will be this term will become V4. Okay. Similarly, V4 is less. Similarly, uh, V1 is less. So actually, it will be V1 by V2, whichever is lesser. So that term. So V4, say V2 by V1 is equal to V3 by V4, like that. Okay. If this is the case, then these two terms will get cancelled. If these two terms gets cancelled, then your efficiency of the Carnot engine is nothing but 1 minus capital T2 by capital T1. Okay. So efficiency is equal to 1 minus capital T2 by capital T. So will you be able to derive the efficiency of Carnot engine now? See, there is some work done happening at each process 1, 2, 2, 3, 3, 4. And we have proven that work done in 2, 3 is equal to work done in 4, 1. So, adiabatic process, one is work expansion, one is compression. So, those two work will cancel out each other, right? So, when the work here it is getting cancelling out each other, so whatever is the heat given here, that is this work. Okay. Q1 is this work, Q1 is this work, and Q2 is this work. Yeah. So this heat is equal to this work, this heat is equal to this work. So here in efficiency term, you just Q1 as a work done, you replace it, because whatever heat you are putting, that is doing the work. Okay. So that, because there is no change in internal energy, right? In isothermal process, whatever you are putting heat, that is doing the work, where temperature remains constant. That's why heat and heat input is equal to work done in isothermal. So that's why instead of heat, you are putting work, right? So you are giving away this much of work. You are doing this much of so Q2 is nothing but this much of work. Q1 is nothing but this much of work. That's why in isothermal, Q1 is equal to this much of work. So this, from this heat, you are relating heat to work here, and you are able to derive the frequency, the efficiency. Okay, now you should be conversant with this PV to the power gamma. Suppose in your entrance, there will be questions like in JE and all. So PV to the power gamma, remembering that is very important in adiabatic. So if it is PV to the power gamma, again how to make the relations between TV also. Like that is relationship between pressure volume, then you can convert into temperature volume. That can be there can be questions like that, and also there can be questions: what is the work done in adiabatic process? What is the work done in isothermal process? And and in isothermal process, PV is equal to constant. So all those things, there can be n number of numericals on this. It is important you understand the concept. Once you understand the concept, you can solve hundreds of numerical. Okay. Nowadays, everything is MCQ. So first, if you understand how the formulation is being done, you can solve n number of numericals. Okay. So with that, we have come to an end of on your chapter on thermodynamics. Okay. So we'll look into chapter on fluids next. Okay. Fluid dynamics. Okay. And fluid statics and fluid dynamics. Okay. Thank you.